I hope you're all having a great evening. I am Mr. Ish. Thank you for joining me. We have something here on the surface which would seem rather intuitive, or you would think that what it would be the point of doing something like this, an exercise such as this. But in essence, it's a worthwhile exercise. We have to prove the shortest distance between a point and a diagonal line, any diagonal line, is always a straight perpendicular line. What exactly does that mean? We're looking here at a point, we're looking at a diagonal line. What would be the quickest distance between this point and this diagonal line? We are saying it's another straight perpendicular line. And why would that be the case? You can visualize exactly what it is we're talking about. If you have a particular point, let's call this P, and you have a diagonal line at whatever orientation, if you want to get from this point to anywhere on this line, the quickest route would be a perpendicular line, a straight perpendicular line. And you see that we have a line and we've drawn a segment from that point, or a small line, but it's perpendicular to it. It's at 90 degrees. Consider another point, and remember it's a point connecting to a diagonal line. We're not trying to connect a point to a horizontal line, but a diagonal line. And let's consider a line which looks something like this. I want to get from this point to this line the quickest, shortest route. I must draw a line which is perpendicular to that, and it's a straight perpendicular line. We have to prove in this specific instance why is this the case, and I will show it to you. To actually show you the reason, we don't have to look at this type of representation anymore. Just consider that you're drawing a specific point, take another line, and we'll consider this our line. If I'm telling you that the shortest route from this point to this line, anywhere on this line, but the shortest would be a straight perpendicular line, you have to take that as face value that that indeed is true. But if supposedly you would not agree with that, then you would connect to anywhere else on this specific line. Imagine this point is A. To connect from point P to this point A, I'm drawing a straight perpendicular line, but you don't agree with that, or someone doesn't agree with that, and they say there's probably another route that's shorter, and they'll pick another point, and supposedly that point right here is B, or they could pick a point and that could be C. And then when you start connecting P to B, or when you connect P to C, you end up seeing that they are indeed straight lines, but this angle here is no longer 90 degrees. It's a certain angle, and this angle inside is a certain angle, but none of these angles is 90 degrees. Like this angle here is 90 degrees and this angle is 90 degrees. When you compare the line from P to C, you have another angle, and you have another angle on this other side, but they're not 90 degrees, and these are not. This line right here and this line right here are not perpendicular. They're straight lines, but they're not perpendicular. And moreover, they're not shortest routes, there will be longer routes. And the reason for that is what I'm going to tell you next. The shortest route from a point to a diagonal line, any diagonal line, must be a straight perpendicular line for the following reason. Take again the same point and draw right here to this specific point a specific line. You know it's 90 degrees. Someone else says no, it has to be point B, and they draw a line. I'm just making it dashed or dotted just for contrast. That's the only reason. What's the difference between this line and what's the difference between this line? Well, when I look at this entire representation, I've created a 90-degree angle, and I've also created a right triangle. You know you've created a right triangle, and there are specific components of a right triangle which are visible. You have a specific leg over here. You have another leg over here of a right triangle. But what stands out is this fact right here. This specific side over here, which is a straight line, P to B, it's a straight line or a straight segment, but it's a hypotenuse. It's no longer a leg. And what do we know about hypotenuse in contrast to the legs of a right triangle? Well, if you want to call this side A, you want to call this side B, you want to call this side C, we know there's a specific theorem out there, the Pythagorean theorem, a squared plus b squared equals c squared. In all instances for a right triangle, the dimension C is always larger than A. The dimension C is also larger than B. If the straight perpendicular line is considered A, or it could have been B, this could have been B, and this right here could have been A, the dimension A. If the straight perpendicular line from your point to your diagonal line is a leg of a triangle, right triangle, and you can call it A and B, you certainly cannot call it hypotenuse. By definition of a hypotenuse and the definition of the properties of right triangles, this must be the shortest route, because any other route is not at a right angle, it's not at a perpendicular, and it will always be considered a hypotenuse, and it'll never be a leg. And that right there would answer the specific question, and that right there would prove that to be the case. The shortest distance between a point and a diagonal line is a straight perpendicular line, because that straight perpendicular line ends up being a leg of a right triangle. And by definition, the leg is always smaller in distance. I'm doing like a segment, it's smaller in distance than a hypotenuse. And that answers our question right there, and it proves it to be the case. From point P to any point on the diagonal line which is not perpendicular, that line will always be a hypotenuse. It can never be a leg. The straightest distance from the point to that line at a perpendicular must always be a leg, and it cannot be a hypotenuse. And that proof over here has been completed for you. If there are any questions or there are any comments, please feel free to leave them and I'll get back to you. Thank you for watching. Have a great night. Bye.